Now that we've started looking at finding maximum and minimum values from a graph, I'm going to give you an extreme value theorem. The extreme value theorem tells us that if we have a function and it's continuous and it's on a closed interval, then there has to be both a maximum and a minimum somewhere on that interval. It could occur somewhere on the interval, or it could occur at the endpoints. That's not to say if it's an open function that it doesn't have a maximum or minimum. We just can't be certain. So if you look at these two pictures here, notice that on this first closed interval, my minimum value is here at my endpoint, my maximum value is here at my other endpoint. So I could determine what my x value is and therefore what my y value is for this point, and same thing here. However, if I look at this open interval, I don't know. I see that my minimum value is close to here. My maximum value is close to here. So my minimum value isn't quite x equals -2. So where do I draw the line where that open circle starts? Is it at x equals -1.9? Is it at x equals -1.99? X equals -1.999? So as you can see, there's a lot of ambiguity involved. So that's why we can't necessarily say that an open interval has to have a maximum or minimum. Again, it doesn't mean it doesn't. It just doesn't have to. Whereas a closed interval will have a maximum or minimum somewhere on that interval. So we're going to start looking at how do we find maximums and minimums. Well, before we talk about how to find maximum and minimums, we're going to talk about another important concept that will be involved in finding maximums and minimums. And that important concept are critical numbers. Critical numbers are numbers that make, or x values that make the derivative 0, or x values that make the derivative not differentiable. So if you remember from the previous unit, we talked about how our functions are not differentiable if they come to a point or if the limit can't be found there. So if something's happening to make them discontinuous, like a vertical asymptote or a jump or something of that nature. So if I'm not looking at a graph, how can I figure out where a function is not differentiable? Well, all we're going to do is look at what values would make the function undefined. So we'll find values that make the function undefined. So oftentimes you'll hear me say, not necessarily can you find all values that make the function's derivative 0 or not differentiable. You'll hear me say what values either make the derivative undefined or make the derivative equal 0, make the function, and it should say the function's derivative. Sorry about that. So let's look at a couple examples of finding critical numbers. So looking at example 1, I have to figure out where is either my derivative 0 or undefined. So the first thing I'm going to do is I'm going to find my derivative. Well, I see I could use the product rule here, but I would prefer to distribute that x squared in and then just use the power rule. So I'm going to go ahead and say g of x is just x to the 4th minus 4x squared. Therefore, g prime of x, I'm going to move it down here to give myself a little more room, is equal to 4x cubed minus 8x. So now if I set my derivative equal to 0, I get 0 equals 4x cubed minus 8x. I can go ahead and factor out a x. I can actually factor out a 4x, and notice that there isn't going to be any values that make my derivative undefined here. So 0 equals 4x times x squared minus 2. So I'm going to say where does this, what values are going to make my function 0 here? Well, I see if x equals 0, I get a critical number, and if x equals either, I can go ahead and solve this for you, but I would add 2 and then take the square root, remembering to say plus or minus. So, or x equals plus or minus square root of 2. Make sure if you're not sure of how I got this result that you talked to me in class. I'm going to assume we're all very comfortable with solving quadratic equations at this point. So there will be my 3 critical numbers. I'm going to go ahead and look at my second example, or again, I'm finding all my critical numbers. So now I have, writing this a little better, I have x plus 2 over x minus 3. So to find my derivative, I see I'm going to have to use my quotient rule. So I'm going to, because I have so much room up here, I'm going to set my quotient rule up here. So my top function is x plus 2. The derivative of that is just 1. My bottom function is x minus 3. The derivative of that is just 1. So going ahead and saying the derivative of the first times the second. So 1 times x minus 3 is x minus 3, minus the derivative of the second times the first, 1 times x plus 2 is just x plus 2, all over the second squared. Cleaning this up a little bit, I can distribute my minus sign here. And I get x minus x, so my x's go away. Negative 3 minus 2 gives me negative 5 over x minus 3 squared. So I'm going to go ahead and set my derivative equal to 0. Well, remember when we talk about fractions, the only way a fraction can equal 0 is if the top equals 0. Since negative 5 will never be 0, I realize that I'm not going to have any critical numbers that come from when my derivative equals 0. However, I do know that I'm undefined if I have a 0 on the bottom, so I also see that this function here, this derivative function, will be undefined if x is 3. So I'm going to go ahead and say I have a critical number at x equals 3, and that's my only critical number. So, summarizing again just what critical numbers are, we're finding any points that make the derivative either 0 or undefined. So make sure the first thing you do when you're asked to find the critical numbers of a function is find the derivative of that function. Remember that may involve using some of the rules we talked about in our previous unit, so watch out for things like product rule, quotient rule, chain rule, or a combination of more than one rule. Once you've found your derivative, make sure that you're setting your derivative equal to 0 and checking to find what x values make your derivative 0, and looking for any numbers that would make your derivative undefined, especially if you're given a denominator.